So far we have learned all the main techniques for differentiations, namely the chain rule, the product rule, and the quotient rule. But there's another technique which is called implicit differentiation, which is quite important to talk about because sometimes we may be given functions that are not necessarily explicit in terms of y. So an explicit function of y in terms of x would be something like this: x squared plus x plus e to the x. It is explicit because we can express y solely as a function of x. But you may be given examples such as the unit circle, which is not necessarily a function per se, but you may be given something like x squared plus y squared equals to 1. Now, y is not expressed explicitly in terms of x. So obviously, you cannot really differentiate this using the standard methods, but in some cases, you can perform some manipulation and say that you have 1 minus x squared, and then you will get y equals plus or minus square root of 1 over 1 minus x squared, and this will become plus or minus 1 minus x squared to the power of half, because essentially you can represent a square root as a power of half, or any root really. If this was root 4, you would write the power 1 over 4, and this is much easier to solve using the chain rule. So you can pretty much solve this using the chain rule if you wanted to find the derivative of that. But the main issue is that sometimes you may be given functions that you cannot separate like this. So you may be given functions where you have a nonlinear term of y in the function, and in such cases you cannot perform a separation like this. So what do you do in such cases if you want to find the derivative of y anyway? Well, there is a method called implicit differentiation which works like this. I'm going to give you an example. Let's say you have sine of y, so sine is a function of y, that's a nonlinear term, x squared, and y is going to be the function of x, so that's what we're going to be solving for. Plus 3xy equals to 1. Now, if y was not present in this term, we could easily just move all the x terms to the other side and then take the inverse of sine, which would be arc sine, and then we would get an explicit expression for y. But in this case, we cannot do that because we cannot really separate a linear term of y from a nonlinear term of y contained like this. So what can we do to solve this? Well, there's a little technique which we already learned, which is the chain rule, which tells us that if we have a function of x within another function of x, namely f of some function like this, oops, not g, that's not the function I was thinking about, it should be f of y as a function of x. So this is the general case we have here. We have some function that contains the argument in which the argument is y as a function of x itself, like in this case. In this case, f would be sine, and we have, because we have y inside as the argument. So the chain rule tells us that we can easily integrate this by first taking the derivative of the outside with respect to x, and then taking the derivative of the outside with respect to y. And we can rewrite this as dy dx df over dy. So this is one way in which we can express that. So in this case, what we're going to be doing is, well, we're going to apply the differential operator to the whole thing, and because this is a linear operator, when you apply it to a whole equation, it will act on each of the functions individually. So we're going to end up with the expression d over dx as of acting on sine y, x squared, plus d over dx acting on 3xy equals to d over dx acting on 1. So what is this going to become equal to? Well, here we have a product of two functions, so we need to use the product rule. So let's differentiate x squared first. We're going to have 2x times sine y plus the derivative of sine y times x squared. So x squared times the derivative of this. So If we employ the chain rule, what are we going to get? Well, the derivative of the inside is just dy dx. And the derivative of the outside with respect to y is going to be cosine of y. So this is the first term here. How about the second term? Well, product rule again, because we have a function that is a product of two functions, 3x and times y. So first one is going to be derivative of 3x is 3 times y plus the derivative of this with respect to y, which is just 1. So that's just going to be 3x times dy dx, because remember that because y is a function of x, we need to use the chain rule, which means we're going to have the derivative of y with respect to x times the function outside, which is in this case just a constant 1, acting on it with respect to y. So that's what we're going to get. And then on the other side, because we are taking the derivative of a constant, we just get 0. Now what we can do is we can move all the terms to the other side. We only care about the term dy dx. So we can separate it in this case, because essentially the derivative is going to be implicit, because it is going to be a function of both x and y. We cannot really separate x and y in this case, so this is the best we can do. So we're going to have dy dx times x squared cosine of y plus 3x, and if we move the other terms to the other side, we're going to get minus 3y minus 2x sine y. So now if we take this term divided on the other side, we get the implicit derivative. The implicit derivative dy over dx is going to be equal to minus 3y plus 2x sine of y over x squared cosine of y plus 3x. And this is going to be the solution for this particular derivative. So you have seen that by implementing the chain rule in conjunction with implicit differentiation, so just applying the differential operator to the whole equation, we have derived a function for the gradient of y, or just the derivative of y, in terms of both y and x. So this is a very neat and very important method to know how to implement, because it is also going to be useful in deriving the derivatives of inverse functions that we will see in future videos. But for now, I'm going to show you another example of where and how this might be used. So implicit differentiation can be very useful in a lot of different cases, not just for these types of functions that we just saw. So let's erase all of this. Now for the second example, I am going to have y over x cubed plus x over y cubed equals to x squared y to the power 4. Now before we differentiate anything, it's better to get rid of those terms in the denominator, so we can multiply everything through by x cubed. So we're going to have, and then everything through by y cubed as well. So y4 plus x to the power 4 is going to be equal to x cubed times x squared, that's x to the power 5, and y to the power 7. Alright, so let's apply the derivative to the whole thing. So for the first case, we're going to differentiate this function with respect to y, so that's 4y to the power 3, and we're going to multiply that by the derivative of the inside, which is dy over dx. Then for this one we have 4x cubed, and on the other side we're going to have to use the product rule, so that's going to become 5x to the power 4 times y to the power 7 plus x5, x to the power 5. The derivative of this is going to be 7y to the power 6 times dy over dx. So now that we have our terms here, we can separate them and solve for dy dx. So what's that going to give us? Well, if we move everything to this side, we're going to have dy dx 4y cubed minus x to the power 5 So I'm going to put the 7 at the front so it looks neater. Y to the power 6 equals to 5x to the power 4 times y to the power 7 minus 4 times x to the power 3. And finally, we have dy dx is going to be equal to 5x to the power 4 y to the power 7 minus 4x to the power 3. And this is going to be over 4y cubed minus 7x5 times y to the power 6. So I'm just going to scroll down so you can see this a little better. So that's our derivative there. Okay, so that was a very nice example. We can see that we can algebraically manipulate the equation at first before we apply the derivative, the differential operator to it. Another example of this. So now we're going to employ something quite interesting. So I am going to use the same technique, but what I'm going to do now is I am going to have a function. So example 3 is going to be the function y equals to the power of 2x. Now, obviously, we have learned how to differentiate functions of the type x to the power of n and also e to the power of some function of x. We know how to differentiate those. But what happens when you have a constant to the power of x, or a constant older than e? Well, things get a bit more complicated, but they can actually be simplified quite a lot. And if you have some intuition about logarithms, you will know that you can actually take that x down by taking the natural log of both sides first. So the natural log is going to take that x down, and then we're going to have natural log of 2. So this is just going to be a constant. And now if we differentiate both sides, we can solve for dy dx. So what's going to happen here? Well, what's the derivative of natural log of y with respect to y? Well, remember that the derivative of the natural log of function is the derivative of the function over the function. So derivative of y with respect to y is 1, and the derivative, and the function itself is y in this case. So that's that part. And this is going to be multiplied by the derivative of y with respect to x by the chain rule. So that's that. And then the derivative of this side with respect to x, well, that's just going to be ln 2, because this is a constant and that's just x to the power of 1. So this is what we have so far. So now what we can do is we can rewrite dy dx equals to y to the power of not to the power, times natural log of 2. And you might be wondering, well, what do we do now? Because we have the derivative as a function of y but not x. Well, we know what y is because originally we were given a function that is explicit of y. So we're just going to substitute back into it. So y is equal to 2 to the power of x times natural log of 2. So this is going to be our derivative. So this is one of the many other applications that implicit differentiation has, and I really recommend you to think about problems like this and see how you can manipulate it algebraically before applying the derivative to it and finding a solution for it. In the next video, we're going to learn how to use this method to find the derivatives of inverse functions such as arcsine and arccos.